Okay. Before we continue to 13.3, so the last discussion we have discussing the 13.2 here, the derivatives and integrals. So we have learned that suppose we have the three-dimension space, x, y, z like that, and we will have two factors, and by definitions, if we are moving the position from this point Q, so if we move this Q closer to P, then we will have this R prime or the derivative. And you can see from this triangle that we will have the tangent, right? And from the tangent, we will say this is the tangent vector, right? And because it's a vector, we also have the unit tangent vector, which is this T, the capital T, okay? This you need to keep in mind, okay? And then we also have some set of rules for differentiation. But I think let's just see the last three here. We'll have the dot product, the cross product, and the chain rule. If you have direct questions, okay? So if you have direct questions about dot product or cross product, my suggestions is evaluate dot or cross, then derive. So you don't need to be worried about this whole expansion here. Okay, if you are just finding the dot first, you will get much more simple equations, and then you can derive easily, rather than you are expand into these two product rule, right? So it is depends on when you are going to need this expansion. Okay, but my my preference is you can just evaluate the dot and cross first, and then derive. And we also learn about the orthogonal. So if you have the value of the vector, if it is a constant, then of course all the way the R prime will be orthogonal to the vector. And then we are set to learn the integrations, and all the conclusion is the same. What we need to do is just derive each component, integrate each component. Okay. Now let me give you some example for derivative and how to find the tangent. Example for 13.2. So you have vector functions R, and that's the equation. And it start from 0 to pi. Find the point on this vector functions, and you have the parameter t is from 0 and to pi, where the tangent line is parallel to plane So first, you need to see that the tangent line on this vector functions is parallel, okay? Okay, meaning it has the same directions. Okay? It has the same directions to this plane. Okay, so at least now you can write the directions. Usually the directions for the plane we can write in n, okay? The direction numbers based on the plane equations is square root of 3, 1, and there's no z, so 0. So let me write one more time. The r is 2 cosine t, 2 sine t, and e with the power of t. Now the tangent will be negative 2 sine t, 2 cosine t, and e to the t. Okay. Now, how do we get the conclusions that this is parallel? Now we can write down that because of the parallel, because of parallel, tangent line and plane. Then we can say, okay, the tangent vector r prime, you're right, orthogonal to planes normal vector. Okay. Let me. Okay. So first, because the tangent line is parallel, so let me draw maybe here. So let's say this is the tangent line, and this is the plane. So meaning, if you have the it's not tangent line, sorry, it's a vector. So the tangent line will be here, for example, at this point, and it's also orthogonal to the plane, right? This is just an example. Okay, so we can write that the so r prime t dot n should be 0. Okay, from here. So we can calculate and this should be 0. And what we need to find is we need to find which t we will calculate the t. Okay. So -2 square root of 3 sine t plus 2 cos t, and then the other one is 0, so it should be equal to 0. And we will have tangent t is 1 over, or we can write, and because t is from 0 to pi, so t will be pi over 6. So at t pi over 6, we will have positions, vector positions. Okay, vector positions. So 2 cosine pi over 6, 2 sine pi over 6, and e pi over 6. So we will have so point P will be that's our point. Okay. So this is the point where the tangent parallel to the plane. Okay. If you have similar questions like this, maybe in quizzes or any exam, the point here is you need to, the more complete your answers, like you write your reason, like you can just write like this, it's parallel. Or maybe at the first, you can write that the tangent and plane is parallel. And then write this, the orthogonal, and that's already complete reasoning. Okay. If you maybe not writing the reason, maybe not really full point. Okay. Okay, maybe one more example, and then we can move to the 13.3. You have any questions here? If no, let me just write another example. So the graph of R1t and R2t, the graph intersect at the origin. So find the degree of acute angle between the tangent line. To the graph of R1 and R2 at the origin. The R1 is tangent inverse T sine T and T squared. Okay, let me give you some time to think and maybe try to solve. So the question is asking the angle theta. So the question is asking this acute angle. So acute angle means the angle between 0 and 90, okay? 0 and pi over 2. So if you confuse what the questions is, it's so the angle is in between the tangent lines, okay? Between the tangent lines. So the angle is between, let me write here. So the angle is between R prime 1 and R prime 2. And origin means if you have a space, origin means this point, this origin. Okay. So anyone find the angle? Anyone find? What's the angle? Find the first. Find the at the origin. 0, 0, 0. Find the origin. 0, 0, 0. Now we need to Okay, so maybe I'm just writing the derivative first from the tangent. So this will be 1 over 1 plus t squared. This is cosine t and 2t. And the R2, the tangent is 2t minus 1, 2, and 1 over t. Okay. Now we need to be careful. Okay. Now the question is asking, the point is to be at origin. Okay. So what you need to do is you need to find so find t so that R1 is 0, 0, 0, and R2 is 0, 0, and 0. So we will have different t. So we will have different t, right? So R1 will have T1, R2 will have T2. So from R1 here, the T will be 0. T1 is 0, right? From this R2, T2 is 1, right? To make it 0, 0, 0. Okay. So that is the T that we will evaluate in our tangent. So for R1, we will evaluate at 0. it will be 1, 1, and 0. And for R2, we will evaluate at 1. This will be 1, 2, and 1. Okay. Now we need to use the or let me write in terms of R1 and R2. Okay. And this will be we can write this the dot product between these two. So 1 plus 2, right? So 3. So 3 divided by this will be square root of 2, square root of 6, right? So we will have square root of 2 and square root of 6. So 3 square root of 12, or this is 3 or we can simplify. Okay. So theta is pi over 6. Okay. I think that's enough for the example, and we can move on to the next section. Okay. So so the next section is the 13.3. So this will be the arc length and curvature. Let me remind you what is arc length means. So if I have curve, let's say we just have 2 dimensions like that. You just have 2 y and x. The arc length means is we need to measure this whole, so measuring length, right? And how do we measure the length? We are measuring the length by dividing the line. So maybe divide here, here, and connecting all the line like that. Okay. Or if we want to make it in more clear sense, in each point we will have the tangent, right? We will have the tangent. Let's zoom in the tangent. Okay, so you have the angle there. You have the y and the x, and you will have, let's say it's the dl. What arc length means is if you have the dl here, and you have all the dl from, let's say, from A to B. Okay. let's say this is x equal a, this is x equal b. So you have dl for that interval. So arc length means is you are integrating this dl, right? And the dl, we can find the dl through just a Pythagorean formula, right? And then we can also use this similar concept in parametric in chapter 10. We just finished, right? Chapter 10. So in parametric, we have the L is integrations. Let me just write all terms. Okay, we have that. Okay. Now in the space curve, in the 3D space, we will also have the similar similar formula. And similar way. So we define this, and we are measuring the length by adding all this the tangent. Okay. So this is a curve C, and let's say this is in a vector that has 3 components. Okay. So length of space curve is the limit of length of inscribed polygon. What we did, again, what we did before, the same. And the restrictions or the requirement is if the curve is traverse or move, okay, or move exactly once as the increase from, let's say, any point A to B, then we can write the uh, the equations. It's L and all this we can also simplify, becomes the value of the R prime. So you need to remember that the curve cannot be a loop, cannot be going back to the original point. If that's happened, what you need to do is you need to cut. Okay? You need to cut. Maybe you need to set the t maybe half. Okay? So for example, if you have like this, and maybe this is symmetrical, but you need to find the length. You need to cut. So maybe you just evaluate this and then evaluate this. So this is 1, 2. So you need to make sure the curve is moving once, okay, and not going back to the point previously. Okay. And of course, this f prime, p prime, h prime all need to be continuous. Okay, it need to be continuous. You can also write the parametric equations. X is ft, y is gt, h is z is ht. Okay. And a single curve, it can be more than one function. Okay, so single curve can be more than one function. For example, if you have example in the twisted cubic, you have it's called twisted cubic. You can try to find what kind of graph is there, and we can also uh, represent in terms of okay, so this is P E U. So we can explore the curve by more than one function because the L is independent of variables, right? So we can explore with many functions. Because L is just the length, right? Just the length. So it's independent. Or we can say also L is a geometric property. Okay. And now the second sections in arc length is arc length functions. So arc length itself is a length geometric, but we also have arc length functions. Okay. So we want to take the arc length into functions. Okay. It's similar to what we have done before. So we are cutting the length into a segments. Okay. Into a segments. Now suppose we have suppose um, we have RT and then the t is from A to B. R prime is continue, and C is the curve that R is traverse exactly once as the increase from A to B. But maybe I need to move this to the right side. Here. Okay. So the arc length function, we define the arc length function in terms of S. Okay. From some point until t is our variable. Arc length, from what you have learned, we usually use x, right? And now we change to t. And inside, it's another variable u. So we have two variables, u and t. R prime, a value of R prime is the same as what we write before. So we can also expand this into the equations. So we can write this is dx over, now we have du, okay, plus and this is integrated with respect to du. So let's say this is the R, let's say RA. Okay, so this is A at A. And maybe um, we have this. This is at some t. Yes, it can be any t. So we can set up RT like that. So with this is will be our arc length functions ST. Okay. So this is the way how we are saying the length in terms of variables t. Okay. Okay. Now let me copy the equations, make it smaller. Okay, now if we take derivative of this function, okay, take derivative of this, with the fundamental theorem of calculus. And this is actually our r prime t, right? So the whole thing here becomes ds over dt equal we are usually write this ds over dt as or let me use the terms useful or helpful to parametrize. Parametrize the curve with respect to arc length. So why we need the arc length functions? Because arc length itself is, like I said before, it's geometric, it's independent. So if you want to make observations on the some curve, the length of the curve, if you want to take some simulations there or some observations, we can take the approach that we can make the arc length as a function. Okay. So for example, if you want to reparameterize, let's say the helix with respect to arc length from point 100 to in direction of increasing t, meaning this is the A, right? The initial point. So initial point A is 100, which means t is from 0, right? According to the RT. So RT is cos t. I will write in terms like this. So R prime will be negative sign cos t and 1. So if you want to check the ds over dt, we can check the value of R prime. And this will be square root of 2, right? And we have st from 0 to t of the R prime u du. This is square root of 2 du, or we can write this as square root of 2 t. So from here, we get s is equal this, right? Now we can exchange this into a new parametric s over square root of 2. So this is the way we reparameterize. Okay? So we can use with more than one function to have more connections. So if you have some data sets and you want to evaluate or reparameterize some set of length, you can also use this way, okay, this approach. So we can also use this to reparameterize the whole functions with s over square root of 2. So we will have so r will be cos and the way we are seeing this approach, we can connect to many functions. Okay? So if we have a lot of connections in functions, we can have a lot of parametric to visualize, okay, how the graphs looks like. Okay. It's somewhat maybe the point is why we need to change the t into the s. In case you are maybe dealing with more simulations, right? In terms of visuals in graphics, sometimes you need to relate to other parameter to see what is really going on in your graphics. So this is called the method is called the reparameterize. So we have a parameter t, and we set up a new parameter. It's called the s divided by square root of 2. How we are setting up that parameter is through our arc length function. Okay? And at the end of the day, we have a new set of parameters. This is the one that I said before, that the curve, it can have like more than one function, because arc length is just length, right? It's a geometric, like this may be 1 meter. It's just 1 meter, a constant, right? But if you are going to say, I'm going to here, but I can go into here and here and here. So I can have a functions, right? So this is one way to show that the arc length can be cut into segments. And in that segment, we can set many parameters. Like for example, this parameter s, and then we can set another parameter if you want, and we can have many more set of parameters. Okay, and that is the arc length function. We will going to move forward a little bit to the. It's called the curvature. Okay, so now the new terms for you is the curvature. Okay, let me write for you. So the curvature. If arc length is measuring the length, right? It's measuring the length of the curve. The curvature is measuring the smoothness of the curve. the terms usually write as the curvature. Okay. And now maybe you are thinking, what's the definition of smooth? Okay. So what's the definition of smooth? Definition. So let's say you have a curve, okay, like that. And you have, which one is smooth? Left or right? Right one, right? This is, let's say this is smooth. Smooth is low. This is smooth is high. Okay. So smoothness, let me just write first, no sharp corner. In the easy way, no sharp corner. Or if we want to write more official, the curvature Okay, so on interval, we call it smooth if the r prime or the tangent is continuous first, and the tangent should not be 0 on that interval. So maybe you have maybe that way. And maybe you have the tangent. Okay. So if this is the tangent here, so it has no sharp corner, no sharp corner. And then when tangent turn, it does so continuously. There will be nothing that affecting the smoothness, like it is turns really well. Okay. Okay, if you have P, the unit tangent vector as this definition. Okay. If you look at this, okay, when it's a little bit more to a little bit straight, right? It turns like slowly, right? But when it does bend or twist it here, the curve, the vector, the tangent, it goes faster, right? This is going slow there, but here it's going here last. Okay, it directly goes changing the direction. Okay, okay, see the difference. Okay, now uh, from there, the curvature, okay, the curvature at a given point in curve C, okay, is okay a measure on how quickly the curve change direction at that point. Okay, remember that. So this is slow, and from this one, the bending one, it's going faster, right? Meaning there's difference in the curvature. Okay, so how smooth we can tell is how quick the curve change. Okay, so we define, because now we already know that the all things here is basically our arc length. So basically, what this graph is telling you, or and this definition is telling you, the curvature is the change of. We are using this unit tangent factor, okay, because it's uh, already applied the tangent. Okay, so the unit tangent factor. So the change of unit tangent factor with respect to the arc length. Okay, or you can write down the curvature is equal. So curvature is magnitude of rate of change of the unit tangent factor with respect to arc length. So T is unit tangent factor. Okay, this is the first definition. And from this definition, okay, so from this definition, we can create connections to our previous equations. Okay. Let me move to here, and let me write one more time. The curvature is okay. Now we can write down the dt over dt with chain rule, right? Chain rule. So we can connect to dt, and then from here we can also see the connections. Okay. And this ds over dt is what we have from the arc length before, right? So the curvature, we can write the curvature also in terms of this is become t prime t, right? So t prime t, and then below is r prime t. Okay. Maybe I'm adding t. So in a parametric sense, we can write the curvature okay. Okay, the next uh, okay. Since t is and okay, now we have okay, t r prime and this is R prime is just write T and then ds over dt. Okay. Now, if we are evaluate the second derivative of the r prime, and then we derive once more, we will have r double prime, and then we will have the product rule. Okay, the product rule from here, from this fg here. Okay, so we will have okay. Now we want to have connections to the cross. Okay, or maybe I will write first. Um, if you see the textbook, it's not mentioning how you get all the proof, but I will show you why. So because t and t prime t both are orthogonal, okay, each other. So when you have this is equal 1, of course, because the value should be 1, okay, the unit tangent vector, right? So if this is 1, a constant, right? So this will be t prime t plus t prime will be 0. Now, the fact that we are going to use this is we are going to take this into a cross. Okay, so okay, so I'm writing r prime cross r double prime, and then this will become t r prime cross or maybe I will use the same plus ds. and this part is 0 because this is orthogonal. And can have this this is also r prime, so it's squared, and the last will be the, and the curvature is t prime over r prime. And r prime we get from, if we want to evaluate this, and then the cross is sine, right? Sine, and orthogonal is pi over 2. And sine pi over 2 is 1, so this will be this is 1, this is 1. Okay, so we have this. This is not D, this is R, sorry. And this we can substitute there. So curvature will be R prime cross R double prime R prime and then cube. Sorry, it should be cube. Sorry. Oh, sorry, it's here. So it should be multiplied by R prime cube, right? So it will be this. Okay, probably you will be confused with what I'm doing here, but I will tell you maybe later. But and if I don't have time to prove this, maybe I will just show you some notes. Okay. So basically, the curvature, we can also relate the curvature into the first derivative and second derivative of the r. Okay. You can take the textbook if you want for some summary for this equation. But I will maybe tell you later more about this equation. Okay. I think the course is I will stop until here, and I will give you the midterm. Okay, the midterm result. So if you don't have any questions, okay. So I will explain more about this later on Monday.